Oh, okay.
All right. Grand finale, 2022 TMD School. By Professor Michael Engelhardt, appropriately from New Mexico State. And, I noticed we were only about that first and last lectures at school are in person. So I'm grateful that you're here. And Michael will tell us about TMD physics from
All right, thank you very much. Yes, so TMD physics from Lattice QCD. Maybe I should say one thing up front. Fiala, in her lectures, mentioned things called quasi-PDFs and pseudo-PDFs. I'm not going to talk about those because I'll go straight to TMDs. We only have one lecture, and there's only time for so much. Quasi-PDFs and pseudo-PDFs and further methods have been developed to quite a large extent for PDFs, but they're only starting to be used, starting to be expanded to TMDs. So there aren't many results from those approaches to be presented. At the end of the lecture, I'll comment a little bit about what the perspectives for those are. But the bulk of the lecture will be about an alternate approach that I've been pursuing for a longer time, which in a sense, it's similar in spirit to pseudo-PDFs in that one uses Lorentz invariance very decidedly and forms certain ratios of correlators like one also does for pseudo-PDFs. So in a sense, it's most related to that, but I'm not going to talk about those PDF approaches, for which quite a large literature exists already up to this point. I'll talk about directly about TMD physics. And so quite a few people have been involved in this work over the years by now. Let's see whether I can do that with this pointer. So there was this initial group of Bernie Musch, Phil Hegler, John Nagel, and Andreas Schäfer, who started out on this, and I joined soon after when I was on a sabbatical at Jefferson Lab, and I learned about doing this. The second line is the Lattice Hadron Physics collaboration, whom I mostly work with, so they're all involved. The Los Alamos group is involved in these things. More people from Regensburg are involved. We collaborate with Simonetta Liuti and Abba Rajan, who provide phenomenological input and give us great ideas of what one could look at and why and who and how. And also Taku Isoguchi is involved from the side of providing lattice configurations and support of that sort. So yeah, let's start out looking at the fundamental TMD correlator. So this is something you will have seen during this school. This is the basic definition. So what you do, just to remind you, is you look at a bilocal correlator in your hadron state. So these are this would be, for example, a proton state with a certain momentum P and spin S. We look at diagonal matrix elements. So the momentum and the spin here in the bra and the ket are the same. And we look at this bilocal operator. And so in position space, so if you look at a bilocal operator in position space with a separation B, then when you Fourier transform that, it's roughly speaking a number operator for quarks of a certain momentum. So using this type of bilocal operator in position space essentially counts quarks, and you can you can count them in different ways. You can put in a gamma structure, which lets you count in an unpolarized way, or which lets you differentiate between the different velocities they might have. Or well, there's 16 options. Right? There's a basis of 16 gamma matrices, and you also have to put in a gauge link in order to for the operator to be gauge invariant. You have to put in a gauge link linking the positions of the quark operators. So this is the fundamental correlator you look at, and when you define TMDs, you Fourier transform that, right? So here you've got your correlator that I defined above in B space, in position B space, and now you Fourier transform both the transverse, you Fourier transform from this operator separation B to the quark momentum K, both in the transverse direction and also in the longitudinal direction. And that now gives you a momentum space correlator, which has the longitudinal momentum fraction and the transverse momentum. And this is the correlator that defines the TMDs, right? You decompose this, I'll show it in a minute. You decompose this, and that's how the TMDs are defined. A lattice calculation will typically stay in position space, or it'll try to stay in position space as long as it can, because doing this transform is numerically not very stable. You need data on the whole axis in principle, and the lattice never gives you data on the whole axis. So most of what we do is calculating the position space correlator and interpreting that. Since we have this gauge linking here, it brings its own divergences into the game, and those divergences have to be taken care of by dividing by a so-called soft factor. And also, I'm not going to worry for the time being very much about the soft factor, because I'll be forming ratios in which the soft factor cancels. At the end of the lecture, I'll discuss a perspective, and I'll discuss first steps for obtaining also the soft factor. But for the bulk of the lecture, I'm going to show how I form ratios where the soft factor cancels out, and we won't worry about it for now. Okay, so that's the start of the definition. Of course, one thing we now have to talk about is the shape of the gauge link. And as you've seen in these lectures, you don't use the most naive possible thing where you just use a straight gauge link between the positions of the quarks, right? The quarks are at 0 and at D. So the naive thing would be, oh, let's just put a straight link. No, you don't do that. You instead have gauge links going off to infinity from both of the quarks in a direction close to the light cone, or naively you would put them on the light cone. And what it physically means is you've hit a quark really hard. It's a deep and elastic process. And that quark is just kicked out of the hadron really, really fast. In other words, on a light cone trajectory. And what the gauge links are iconal representations of the propagation of the kicked quark. So this it's the ray optics limit of the quark wave that's going out after you hit the quark. And in a lattice calculation, of course, you're never going to get stuff going off to infinity. It's always on a finite lattice. So in a lattice calculation, actually the gauge link has this staple shape where you go a finite distance, you close the staple, and you go back. And so I'm defining the variables here. I'm going to call so B was the operator separation. That's the width of the staple. V is a vector telling you the direction of the staple, and that will want to be somewhere near the light cone ideally. And eta is going to be the length. Yes. So V is like V is a unit vector. I'm separating direction and length here. So V is just indicates the direction, and eta is the variable that gives you the length of the staple. And eventually, we want to let eta go to infinity. And let's see what so far so good. I'll show you how this extrapolation eta goes to infinity works. Now, what about this V, which I'm telling you should be close to the light cone? So that's a problem too. So first of all, even before going onto the lattice, you can't put it directly onto the light cone because you get these rapidity divergences. And I'm sure they've been discussed during this school a lot. So one of the remedies for regulating the rapidity divergences that you have if you put the V onto the light cone is you rotate it slightly off the light cone. So that's not the only way of doing it, but that's the most widespread common way of doing it. And so instead of V being a light-light vector, you make V a space-light vector. And that's the scheme that was put forward by Collins and Rogers and collaborators. And so you have another parameter in this game that characterizes how far you've rotated V off the light cone. And this parameter generically it's what's called a Collins-Soper type parameter. This is not, the one I'm defining here is not exactly the same one that Collins defines, but it's a similar thing. And it's basically the hyperangle. So I'm taking the scalar product of the hadron momentum with the direction that this kicked quark is being ejected into. So, and I'm dividing by the 4 magnitudes. So actually, the magnitude of P is just M. proton. So I'm using the hyperangle to characterize what the rapidity difference is between the hadron and the kicked quark. And ideally, you want this to become really large. In the end, you want to take this zeta hat to infinity. That means that from the point of view of the hadron, the kicked quark is really going off in the light cone direction. So everything we do will also depend on this zeta hat. Now, in a lattice calculation, it's actually very hard to get to large zeta hat, and you'll see.
Just so I understand, B is space-like, is magnitude B1?
Yeah, the magnitude of B is 1. It's just supposed to be, yeah, the unit vector, and I've put the magnitude into the eta. Yeah, yes. Yeah, so this is just, you're right, this is 1, this is the mass, and all the non-trivial information is here, this is in the scalar problem. Yeah, and as you've also seen, there's these interesting TMDs like the Sivers TMD and the Boer-Mulders TMD, which are odd under a change of sign of the eta, right? For CDs, you would be going off, you would have the stable going off in the one direction. For Drell-Yan, you would have it going off in the opposite direction. And some TMDs are such that they change sign when you flip the sign of eta, when you go into the opposite direction. Yeah, so that's the setup. And okay, so we're back to my initial slide. I've now explained everything in here. I've specified what the path of the gauge link is. And so, as I said, this correlator, Fourier transformed, or regulated and Fourier transformed, defines this momentum space correlator, which we decompose into the TMDs. So we use our phi, and the correlator depends also on the gamma structure I'm putting in. So if I take the phi gamma plus, then that gives, and I decompose it into the relevant Lorentz structures, then that gives me the unpolarized TMD and the Sivers TMD. If I take the gamma plus gamma 5 correlator and I decompose into the relevant Lorentz structures, then I get the helicity TMD and one of the worm gear shifts, one of the worm gear TMDs, the G1T worm gear TMD. If I take the I sigma I plus gamma 5 correlator, so these are all the leading twist ones, I get the transversity TMD, I get the pretzelosity TMD, I get the other worm gear shift, the H1L worm gear shift, and I get the Boer-Mulders function. And so those are the 8 leading twist TMDs. And you've seen this, right? Okay, who has not seen this?
They talked about it in Sivers.
I'm sure, yeah, it had to.
The
has to.
comment I make is that lambda is the longitudinal polarization.
Oh yeah, right.
That's denoted as L in the hand.
Yes, right. Exactly. When I wrote that part of the handbook, that's one of the first things they made me change. ST is ST, but lambda is SL. It's the helicity. It's the longitudinal spin. Yes. Right. So you know that, but there is still a good reason for me to show this. So because what happened here is I took the momentum space correlator and I decomposed it. And I don't even need to show you this matrix, you've seen it. More importantly, I can also take the position, if I can do this in momentum space, I can do exactly the same thing in position space. I can take the position space correlator and I decompose it, and it's almost completely analogous. And so here I'm starting to do something that's specific to the lattice calculations. Because as I said, in lattice calculations, I want to do as much as I can in position space. So if you look at the position space correlator instead of the momentum space correlator, all you've done is switched the quark momentum vector, the k vector, for this separation b vector. But otherwise, from the point of view of Lorentz covariance, it's the same thing. Just one of the vectors is different. Instead of k, you have b. But apart from that, you therefore have essentially the analogous decomposition. And if you take the gamma plus position space correlator, you again get something that has to do with unpolarized and something that has to do with Sivers. And instead of the K, you have here the B. Let's go actually up. Yeah, here there was the K, right? It's a K cross S. And now in position space, it's simply the B cross S. So it's completely analogous. And so you can decompose the position space correlators into these invariant amplitudes. These amplitudes A sub number B will be written in terms of Lorentz invariance, and that's an essential thing that I will use. That these are Lorentz invariance amplitudes, and I can calculate them in one Lorentz frame where I like to do Lattice QCD, and immediately transfer them to some other Lorentz frame in which you might like to talk about phenomenology. The notation is might seem a bit funny. These are already linear combinations of more elementary amplitudes that you can decompose in. I'm not showing you here the whole decomposition. It would be much larger. I've already formed appropriate leading twist combinations. It's complex enough, but yeah. So in position space, I can also do these decompositions, right? And so essentially, if I do a decomposition in momentum space, and it gives me the TMDs, and I do a decomposition in position space, and it gives me these A amplitudes, what that means is that essentially the A amplitudes are Fourier transform TMDs. It's not exactly one-to-one correspondence, because when you Fourier transform, you also have to take into account the prefactors, which might have factors B in it. So these are not one-to-one Fourier transform TMDs, but they're at most linear combinations of Fourier transform TMDs. There's a quite direct correspondence between the A amplitudes and the momentum space TMDs.
So yes, you calculate that you can get back to those TMDs easily.
That's the plan. So what I'm going to do now is introduce some notation to make exactly this step more concrete. I'll introduce a notation for these Fourier transformations. So let me just introduce some of these notations. If I take a TMD and I put a tilde above it, then that just means I've taken the standard momentum space TMD and I've Fourier transformed it with respect to the transverse momentum to get a function of the transverse position. Right? So the tilde just means Fourier transform in the transverse directions. You can do a bit more. You can also do a Fourier transform where you've given yourself additional powers of k. So you can do higher moments, you can do higher KT moments. And you would, of course, do that by putting derivatives with respect to B in front. So if you take this here and take a couple of derivatives with respect to B, each derivative gives you down a KT. So you can generalize this to expressions where you have powers of KT in here. And those expressions, the power of KT that I put in here is denoted by the number in the parentheses here. So super parentheses n means I've taken n derivatives with respect to dBt squared. In the limit, so if I calculated one of these, and then afterwards take the limit b going to 0, then the exponential factor is gone, and I strictly have moments, KT moments of TMDs. Right? Now one has to be careful. In general, those diverge because the TMDs don't fall off quickly enough at large KT such that this integral still converges. So in general, these things are divergent. Leaving a finite b, leaving this oscillation in here, regulates that divergence. So the objects at non-zero BT, they remain finite, but if you want to take the BT going to 0 limit, then you will get divergences. And that's also not surprising directly in BT space. In B space, when I take B to 0, it literally means I'm letting the two operators go towards each other. And in field theory, if you put two operators at the same position, that's usually divergent. And that's what's happening here. So you can either say this in B space, you can say, oh, in B space, I'm letting two operators go towards each other, that's divergent. Or in K space, you can say, oh, I'm calculating a K integral over a function which diverges because the integrand doesn't converge fast enough for K going to infinity. Those are two equivalent ways of talking about this divergence. So for the most part, I'm going to keep B non-zero. At one point in the lecture, I will investigate quantities where I do want to let B go to zero, and I'll give the appropriate caveats, and I'll show you that maybe it's not as bad as you might first fear. Okay, but mostly I will keep B finite, and then when I keep B finite, then the oscillatory behavior here keeps this convergent, and it's a much better behaved quantity. Okay, so that's this is integrals with respect to the transverse momentum. Another thing I want to be able to do is integrals with respect to the longitudinal momentum. If I just integrate over the momentum fraction, then I denote that by putting a square bracket 1. So it's the first, this is the first Mellon moment. That's why I'm calling this 1, not 0. This is usually called the first Mellon moment. And almost all the results I'll show, except for something at the end, will be for first Mellon moments. And again, one has to be careful. In principle, when you regulate the divergences, you can or if you translate between different renormalization schemes, the renormalization factors here can depend on X. So again, you have to take this with a grain of salt. But let's say you've calculated this side in Lattice QCD, and you say, well, now I'd like to compare that to some experiment. What you can always do is get yourself some really good experimental data and convolute those with the matching factor. So put your favorite matching factor in here to get to like NS bar or whatever you want to do. And that, so you take the renormalized TMD and unrenormalize it, unsubtract it. That object is then directly comparable to your lattice computation. So there is no obstacle. You really, by calculating this in Lattice QCD, you do calculate a physical thing that can be directly compared to experiment. All I'm telling you is that you might have to be a bit more sophisticated in manipulating your experimental data in order to have a direct comparison between the experiment and Lattice QCD. Okay, so these are the notations. Again, the parenthesis, the super parenthesis tells you how many powers of KT I've introduced, how many derivatives I've taken. The super square brackets tells you that I'm taking a Mellon moment with respect to the longitudinal momentum. And now let me show you the correspondences. So here we are after having introduced the notations. The A2B amplitude is directly the Fourier transformed unpolarized TMD, first Mellon moment thereof, and nothing else. I haven't done any derivatives with respect to BT squared or anything. So I've just taken the unpolarized TMD, integrated it over X, and Fourier transformed, and that's directly the A2B up to the renormalization. So if this is your renormalized quantity, then the amplitude, the raw amplitude I'm getting, say from a lattice calculation, will still have the soft factor in it, and also renormalization factors. I mean, I've absorbed the renormalization factors into this S thing. And so what will happen is, this is the point where I will decide, oh, let's take ratios. And then this stuff cancels. And then I'm really calculating something physical from my lattice calculation. So that's the motivation for taking ratios. This is the step where I can get rid of this stuff. So, okay, another one I have, I'm not showing all of them. The A12B is directly the Sivers TMD, F1T perp, Fourier transformed, integrated over X, and weighted with another KT squared. So I'm taking a certain very specific moment of the Sivers TMD, okay, but that is directly this A12B that I might get out of a lattice calculation. Another one, A4B, is directly the Boer-Mulders TMD, Fourier transformed, integrated over X, and also weighted with one factor of KT squared. And so, and there's of course many more. I showed you, well, there's at least at leading twist, there's 8 here, and you can also go to sub-leading twist. But here's now the final step now is, okay, I'm going to decide to take ratios in order to get rid of the soft factors and give you the physical interpretation of these ratios. And then then we can start to try to calculate things on the lattice. Okay, so what we define are so-called generalized shifts. So as I said, I form ratios of the quantities that I just defined before, in which the soft factors and also gamma-independent multiplicative renormalization factors cancel. Yeah, that's another thing. As long as you keep B finite, you expect the renormalization factors to not depend on the Dirac structure. When you let B go to 0, one thing that happens is now you have some local current, and it will know, the renormalization of that will know about the Dirac structure. So that's another complication when you let B go to 0. So if B go to 0, there's dragons there. But well, we will be intrepid. At one point, I will be intrepid anyway. But anyway, so let's form, okay, let me skip forward one just to show you. Let's form this ratio between A4B and A2B. So this is the Boer-Mulders one over the unpolarized one. According to what we had, I should have put the slides in a different order. According to what we had here, A4B over A2B, that's this particular moment of the Boer-Mulders divided by the unpolarized, right? And that's what I'm saying here. This particular moment of the Boer-Mulders divided by the unpolarized. And here's the interpretation of that. This particular moment of the Boer-Mulders divided by the unpolarized. What is it? If you write this again in terms of correlators, here's your correlator phi again. If you just write down what is it, what exactly am I writing down and integrating? You're actually writing down almost the same thing in the numerator and the denominator, except you're weighting the numerator by a momentum. And so what this looks like is an expectation value of a momentum. And so what it actually ends up being is the average momentum, the average transverse momentum of quarks polarized. Yes, maybe I should use my arms here. So for the Boer-Mulders, you've got an unpolarized hadron. It could even be a pion. It doesn't have to be a proton. But in this unpolarized hadron that's coming towards you, so you're in the 3 direction. So it's flying very fast towards you. And the transverse plane is this plane here. And so in this hadron that's flying towards you, I'm looking at quarks polarized in this direction. And for these quarks polarized in this direction, I'm figuring out the average momentum in the horizontal direction. So you've got this hadron coming towards you. You're looking at the quarks polarized like this, and you're asking, how many more of them are going this way than are going out that way? What's the bias there from which comes from the fact that you've polarized? If you do this in an unpolarized fashion, everything is symmetric, and you won't see any bias, and you won't see any average momentum. But if you polarize that quark in there, then more of the quarks will come out on the one side and on the other side of the hadron, or of the propagation vector of the hadron, as you're counting, as you're doing your counts in your experiment. So there's an average momentum, there's a bias there, and that's what we're calculating here. We're calculating, we're calculating the average transverse momentum of quarks polarized in the orthogonal transverse direction. So yeah, with my arms I was showing, you're calculating the average horizontal transverse momentum of quarks polarized in the vertical direction in an unpolarized hadron. And you're normalizing just to the number of valence quarks. You're just taking the moment of the unpolarized TMD. And so, and now this interpretation is in the limit where there's no more e to the I k b factor. So this is this interpretation is in the b going to 0 limit, which is as I've emphasized a few times now, is a difficult limit. So the physical interpretation is clear in this limit, but the field theoretic quantity is a difficult one to handle. So what we instead generalize, and we define the generalized shift, which is simply the same thing, except we leave in the e to the ikb. We look at this at a general finite BT squared instead of setting BT squared to 0. So that's what we mean by generalized shift. The generalized shift is the one where I'm regulating with an e to the ik. And so these are the types of, this is the type of observable that we can calculate, right? Because we can now directly do a lattice calculation, extract the these A amplitudes. The ratio has gotten rid of all these soft factors and things that I don't know too much about for the time being. And this ratio is directly this ratio of the good old TMDs that you have phenomenologically. And it has this interpretation. And you could take experimental data, and I will actually show you an example at one point. You could take experimental data, which you integrate, manipulate weight in such a way as to form this thing here. And that has to directly correspond to this outcome of a lattice calculation. And as I said, I'll show you examples. So, and you can form many of these ratios, and I'll always put the unpolarized one in the denominator. So basically, I'm doing spin physics here. I'm wasting, or I'm using the unpolarized TMD as the normalization to divide out all the soft factors and all that stupid stuff. And the physics I'm interested in here is the spin physics. So what changes now when I start to polarize things and look at them from certain directions? And so we can do the analogous thing with the Sivers shift. So it's putting the Sivers amplitude instead of the Boer-Mulders amplitude. That then has this now has to be a proton. I take a proton that's coming towards you very fast, and it's polarized in this direction. And now I look at unpolarized quarks in there, and I look at the transverse momentum, at the horizontal momentum of unpolarized quarks in that polarized hadron. So the only difference between the Boer-Mulders and the Sivers is whether it's the hadron I'm polarizing or whether it's the quark I'm polarizing. What else do I have here? Yeah, you can do the same thing with the worm gear shift. So you put another amplitude here in the numerator. You can define a generalized tensor charge. So that one doesn't have any k weighting. It's just a generalized tensor charge in the sense that this is still dependent on BT. And formally speaking, when you let BT go to 0, you get the tensor charge. Except for BT going to 0, you'll have to figure out the renormalization constant ZT. But okay, we actually know how to do that. So these are the types of physical observables we can calculate. And okay, let's do the calculation. So Fiala has explained pretty much how this works. So in the lattice calculation, I directly calculate this type of correlator. I know how to put incoming and outgoing states on the lattice with these interpolating operators that she defined. And I know how to insert operators in between. So I'm calculating a 3-point function. The quark source, the quark sink, and the operator insertion. So I'm doing exactly what Fiala explained. But now this is a quite complicated operator. It's non-local. It has this funny gauge link. So we should look at this in step by step. So here's the diagram again, and it basically just illustrates again what Fiala said. You have a quark source, you have a quark sink. You should make and add an intermediate time tau. You insert the operator. You should make the time differences here large enough such that the excited states decay, all of those nice things. And also coming back to the question by Andrew, you have to put the whole operator at the one time, because otherwise you have this problem of how would you continue from the Euclidean time dependence to a Minkowski time dependence? You just don't know. So you get around that, or the lattice calculations that are straightforward to interpret are the ones where you put your operator insertion at one time. And the staple link that I'm drawing here, this is meant to come out of the slide towards you. So this is all supposed to be still at that one time.
So how do you relate that to the one that you want?
lattice calculates in space-like, in reality, you want its own light cone or
That's-
light cone.
Yes, that's the point here. You use the Lorentz invariance.
Okay.
Because what will happen is I will argue that in the phenomenological frame where all these directions here are certainly time dependent, there's something close to the light cone, that there is always a boost that will relate that phenomenological frame to the lattice frame in which it's all at one time. And by casting my results in terms of invariance, it's trivial to translate the results back to the phenomenological frame. That's
Now, is this fundamentally different from what Jane Dunn does?
yes. Zhang Dang, from the very beginning, from the first word he says, he breaks Lorentz invariance. Because he calls it large momentum effective theory, which means he sets a finite P, and that's not a Lorentz invariant statement. And that finite P is directly his cutoff. It's the central element in his treatment of the field theory. So his very first statement breaks Lorentz invariance. So in that sense, it's a fundamentally different analysis of the same lattice data. Because yeah, Zhang Dang would make you do exactly the same lattice calculation. He would just analyze it in a completely different way.
And you don't have to worry about this other Wilson line, because you just neglect the soft factor. Yeah.
Right. Yes. So in everything I'm doing up to now, I'm forming ratios where I argue that the soft factor cancels, and there are subtleties with that. And Ian Stewart has a lot to say about that. But with a grain of salt at the moment, I'm calculating quantities where the soft factor cancels, and for those I know what to do.
So why do you have one fixed momentum and one fixed position?
Yes, that's I'll say something about that. But there was another question, so I should.
The first bullet point on the right hand side of the equation, where is the dependence on zeta?
The V, right? Here it depends on V. Right. This side I've written as a function of V. This side I've written as a function of zeta. But zeta is simply a function of V and P. So yeah, I've just cast it in terms of different quantities, but it's the same. Right. Okay. Yes. So. Right. So about the momentum. So this is again something which is just lattice technique. So what we want to calculate is a matrix element with well-defined momentum. The momentum is a good quantum number. The momentum of the hadron is a good quantum number. And we want to characterize our states in terms of that quantum number. Now, what you usually do in a lattice calculation, so this is about the choice of interpolating operator. Your interpolating operator to begin with is a position localized object. It's maybe smeared. So this is typically a smeared, but essentially position space dependent interpolating operator that I put. So it contains all the momentum. And also the sink initially is one of these smeared but position localized interpolating operators. And then Fiala had introduced this. What you do at the end of when you've done your calculation, you take your data and you project them onto a momentum, right? If you want momentum 0, all you have to do is just sum over all lattice sites, and that gives you that projects.
Okay, so you actually do a position correlator and do a Fourier transform and fit the momentum, obviously.
Exactly. Yeah, that's all it is. And because of momentum conservation, you only have to do it on one side. It's enough to.
I see.
Yeah. Right. Because then, yeah, it's enough to project this onto definite momentum, because then due to momentum conservation, that's orthogonal to all the other momenta here, and so that's good enough. And if you want, you can put, and if you have a 3-point function, you can additionally put a momentum transfer here. So you project onto a momentum here, you project onto a momentum transfer here, and then by momentum conservation, also the momentum here is then determined.
So you have to then do all these calculations, but all these things smeared all over the lattice.
Yes.
And then
Right.
before you transfer the data
Right.
to get the momentum.
Right, that's something you do in the data analysis at the end. But the lattice calculation gives you position correlators, position correlators. And then in data analysis, you do the transformation to momentum. And you could be projecting onto P here, onto a momentum transfer Q here, and then by construction, this would be a P minus Q.
And this is exactly what Jerry was doing, except now once you get that data, he analyzes it.
Yeah, yes. Yeah. Right. He would then, for him, this P is a central quantity. This P will be the cutoff of his effective theory. Whereas in this approach, the only place where the P really still enters at the end is in the zeta hat dependence. And so, yeah, it's just a different, so Jiangdong goes to a fixed P and uses that to do the whole effective theory thing.
Yeah.
For me, the P is something that I'm working in a Lorentz invariant fashion. And in a sense, everything should be independent of P up to certain Lorentz invariants, like the zeta hat, which still contain that information. So I'm working with the data from a very different approach. And from my point of view, Lorentz invariance is a very powerful and useful thing to keep. So I think Jiangdong is paying a heavy price. And I understand for PDFs and GPDs, you have to do it, because for PDFs and GPDs, they are defined to be light cone correlations. And so you have to find some controlled way of getting from these space-like correlations to a light cone correlation. And for that, you need something like LAMET. TMDs are, by construction, are not light cone correlations. TMDs are space-like correlations because the separation always has an additional transverse component. So you are not forced to do something like LAMET here. In that sense, TMDs are different from PDFs and GPDs. Nevertheless, it's not. You can do a LAMET with this, and the thing that LAMET does for you here is LAMET will allow you to take that B going to 0 limit, which is the light cone limit, in a controlled fashion. And that's the point that I keep weaseling about. So this B going to 0 limit, that's where the big value of the LAMET will be eventually. But as long as I keep B finite, there is no compelling reason to do something like that. Okay, so we're putting the whole, okay, we've probably pretty much discussed everything here. We're putting the whole operator at one time in, because that's what we're able to do best with the lattice calculation. And since the B and V are space-like, so the B is space-like, like I just said, because the separation for a TMD, the separation always contains a transverse component. And that always makes it space-like as opposed to light-like. So the B is, for a TMD, the B is space-like. The V is space-like because I've gone to John Collins and asked him, how would you like to regularize this? And Joe Collins said, oh, let's rotate it into the space-like domain. And, yes, great, let's do that. I think that's a good idea. So B and V are space-like. So the whole operator is space-like. And then a boost exists, which will put the operator at one time. And then I'm happy. Then I'll go to that frame and do the lattice calculation in that frame. Then, since I've cast my results in terms of Lorentz invariance, at the end, when I'm done, I said, but they're Lorentz invariance. They're equally valid back in the original frame, where this staple was actually very close to the light cone, as long as it's still a bit space-like. So that's the other important element here, to write everything in terms of Lorentz invariance. And then I can swap, then I can go back and forth between those two frames. And then, of course, I have a huge number of operators here to try out because I've got all these parameters. I've got the P that I can vary. I've got the B that I can vary. I've got the eta and the V that I can vary. So actually, I'm in a typical lattice calculation here. I'm doing billions of contractions. I'm doing, there's also the Dirac structures. So I'm calculating 3-point functions for billions of cases. And so I can add one further difficulty to what Fiala said. And she said, for example, calculating the propagators is one of the big costs. When you do billions of contractions, actually the contraction cost rivals the propagator cost. So that's another difficulty when you're doing lattice calculations of these types of quantities. There's just so much information you need in order to do your analysis. And then when you have calculated all this whole parameter space of results, then you have to try to do these extrapolations. And well, I'll show you how well that goes. So how much time have I used, Chris? How am I doing?
45 minutes.
Okay, so yeah, that's probably normal.
Okay. Can I go back to so I understand?
Yes.
You said you don't have to insert one P because momentum conservation takes care of the other guy.
Right.
But does the staple kind of break translation invariance, but it's okay because your P is orthogonal to the staple? So you just need momentum conservation in that direction.
Well, you always also project onto something here. And in what I'm doing, since the momenta of the Bra and Ket are the same, I just project this onto momentum transfer 0. But in general, if you're doing like form factors for GPDs, then you would put a non-zero momentum transfer. But yes, the analysis in the end of this contains at least 2 Fourier sums, this one and this one.
Okay.
Yeah. Okay, so this is the first example of the kind of most basic data you get. By the way, so all these data I'm going to show you now are directly at the physical pion mass. Essentially, well, you can fight over whether it should be 135 or 139. This is very new. None of these data are published yet. Until a year ago or so, I would have shown you data at much higher pion masses, at unphysically large pion masses. These are very new data directly at the physical pion mass, so that gets rid of one of the systematic uncertainties. And so what I plot here is I choose a certain BT, a certain staple width. I choose a certain zeta hat, a certain staple direction, and you see how small this value is. That's not infinity. But what I vary is the length of the staple. This is the very first thing I want to do. I want to take these finite-sized staples and extrapolate them out to infinity, because that's what phenomenology really wants. Phenomenology says the quark is kicked out to asymptotia. And so what does it look like? And I'm doing the Sivers shift, because that one's interesting because of the sign change. And let's see, so I'm plotting as a function of the eta, basically. And so you see at eta equal to 0 for a straight gauge link, right? No staple, just a straight gauge link. This is 0, and that's why people initially, when they didn't know about staple links, they thought, oh, there is no Sivers effect, because it's an odd function, and so it's 0 when you have 0 staple length. But when you switch on the staple length, it quickly goes to finite values, and also quite nicely, very quickly reaches a plateau. So this is a very clean, beautiful picture. After 7 lattice spacings or even earlier, you've reached a plateau, and you can pretty confidently say, okay, we can extrapolate this to infinity, and I would say this is the value at infinity. So that extrapolation seems under pretty good control. Yes.
So those numbers are literal lattice spacing. You really just need 10 lattices, about 20 lattice sites to get this result.
Yes, these are the this is lattice units. So if you want physical units, you just multiply this number times the lattice spacing, which is in this case, 0.12 Fermi.
So basically, just the width of the protons enough to keep this sequence like that.
Yeah, this dependence will have something to do with the proton. And at this point, you've left the proton. And, you've reached asymptotia. That's how I would interpret it. And the fact that it's T odd here is not too surprising. So I'm not showing something non-trivial about QCD here. This correlator by construction is T odd. All you have to do to see the T oddness in this correlator is just apply parity transformations, time reversal transformations. So the fact that I'm seeing a T odd result here is merely a check that we've done our calculation right. If in the experiment it turns out that Drell-Yan and cities aren't related by a sign change, then the fault will not be this correlator. The fault will be in the factorization theorem in which this correlator is embedded. So the tests being done of T oddness in Drell-Yan by comparing Drell-Yan and cities are tests of the factorization theorems, not tests of this correlator, which happens to be some small part inside the factorization theorem. So this thing is guaranteed to be T odd, and the fact that we get this nice T odd shape here is simply a nice little check that we've done everything correctly.
One other question: how old is this? Like, how long has this been this clear in the Lattice QCD calculation?
For heavier quark mass, or heavier pion mass, it was this clear 10 years ago when we started. Now, well, I'll give you a sequence.
That's a question about the T oddness. If you go back to the last slide.
Right. Oops. Yeah.
You're talking that when it's purely space line,
Yes.
right?
Mhm.
That staple is a purely space line.
Yes.
So it's not T odd on the lattice. You're flipping it to the other side of the lattice. So
Yes.
it's parity transformation.
Right. It's three.
So does this oddness only appear when you do the transformation from the lattice data to that data? Because there's no T oddness here. It's not
yeah.
parity odd.
Yeah. Well, so basically, I've done a Lorentz transformation which has transformed that into three oddness, the three-direction oddness.
Okay.
But it's simply a Lorentz transformation.
But it's still three. Okay, so it's like, okay, T oddness has become three oddness.
Yes.
And this correlator really is three odd on the lattice.
Yes, on the lattice, this is three odd, but through Lorentz covariance, it's directly related to T odd. Yeah. Yes. Right. So now the reason this is so nice and clean is because, or one of the contributors to this being so nice and clean is because I've chosen a very small one lattice spacing width of the staple. Here's what happens. All I'm going to do now is I'm going to increase the width of the staple, and I'm going to increase B. And so here's the next one. Still looks quite nice. And the next one. And you see you're starting to get, your signal to noise is getting a bit worse. And the next one. Now the plateaus are starting to get iffy. So, but already for a heavier pion mass, already 10 years ago, the plots look basically like this.
You do get different values.
It's in principle, yes, it's remarkably stable. These quantities show no significant dependence on the pion mass, but that was not clear a priori. I will show you an example of
I'm
one.
saying with the staple, the changing the staple.
Oh yes, well, no, actually,
this is less stable. You get a different value.
It does look. I can show it as a movie, right? From large to no, from small to large. So it systematically goes down as you make BT larger. Right? So there is a dependence.
Hold on. Yes, I thought this was a moment.
Yes, it is a moment.
So isn't that something you get by integrating over BT? But to get the moment, you have to integrate over.
I know it's an X moment, but it's as a function of BT.
Oh.
It's not integrated over BT. It's only integrated over X. Yeah, so
it's an X moment.
It's an X. It's only an X moment. Yeah. Well, if you want to view it from position space, it is a KT squared moment of the Sivers TMD.
But that is a function of BT.
But that's yeah, it is a KT squared moment of the Sivers TMD regulated by an e to the IKD, and it's a function of that.
Yeah.
Yeah. So it is the B space. It's the B space TMD, the B space Sivers TMD. Yes. Weighted by KT squared. Yes. So, but yeah, as you see, you can see this as a movie, and as you increase BT, the values change. And let's summarize that. So here's a summarized. Yes. So the infinity limit here is the city's limit. The infinity limit here is the Drell-Yan limit. And if I just plot the city's limit as a function of B, then this is the result. So this is now the city's limit, so only taking the eta extrapolated values as a function of BT. And you see as you, so this is negative, as you increase BT, it becomes, the magnitude goes down. The BT becomes less negative. And so those are the summarized results you get, still at a given zeta hat. I can add a different momentum. I can do this whole thing for a different proton momentum. And this is what it looks like. You know, I have twice the zeta hat. And okay, the curve seems to have flattened a little bit. Things seem to be converging at large B. There's only a significant dependence apparently at the lower B. So what I'd like, so now I'd like to do the next extrapolation. Now I'd like to take all the data as a function of zeta hat that I have. I don't have just the two, I have more. And for fixed BT, I'd like to extrapolate zeta hat to infinity, and then I'd like to plot the extrapolated values. So let's try, yes, so here are some extrapolations. So here I take the smallest BT, I take this small fixed BT, but plot as a function of 1 over zeta hat. That's it. Because we expect these high momentum corrections, we expect them, these are expected to be power corrections. We expect them to be something like 1 over P, or in terms of zeta hat, we expect them to be something like 1 over zeta hat. So I'm plotting it as a function of 1 over zeta hat in order to be able to fit a linear function. And so you see, at least as long as I go to sufficiently large zeta hat or small 1 over zeta hat, you have a very good fit to a linear function. And here's the extrapolated value. Let's do it for the next BT. So here's, or some other BT, I'm not showing you all of them. And again, it fits very well a linear dependency, and you can form an extrapolated value. Here's again a larger one. For larger BT, the fluctuations become larger, but okay, you can still do this. And so, and there's another one. So I can show it again as a movie. Oops, that was too far. There's 4 of them. And I can plot the extrapolated values. So here's the same picture as before. The low zeta hat, the slightly larger zeta hat, and these are the extrapolated ones. And so it looks like this curve pretty much flattens as you extrapolate. But this would be, the green values now are extrapolated in eta, extrapolated in zeta hat. This is now the physical limit. And some time ago, colleagues at Los Alamos, Boer-Mulders especially, he took data from a global analysis by Echevarria and collaborators. So he took the data for the Sivers function from this global analysis and did all those manipulations that we need. He integrated over X and took the correct KT squared moment in order to make that funny ratio, that shift that we defined. And if you take those data and form our Sivers shift, then the value you get is quoted down here. It's minus 0.146 up to, well, with 30% error. And if you look here, 0.146, that would be something like here. It actually seems to work. Who knew? Yes, right. So in fact, the analysis that we did here was, you can show that the Sivers shift for small to moderate BT should essentially be constant. I think also Ignatius Simenia, sorry?
You can't say for large BT.
No, for large BT, right, it's not so clear what can happen. So we used an analysis that should be good at small to maybe moderate BT. And so this value we quote here, as you see, we don't quote the BT dependence. This is supposed to be the small to moderate behavior. And so, okay, small to moderate. So it's maybe a little bit shifted from what we have here. Yeah, these gray shadings that are always put, the gray shadings indicate the region where I don't trust the lattice calculation so well, because the distances are so small that you probably have significant discretization effects. So this gray region is the one where you worry about discretization. But somehow here at moderate distances, okay, this value is maybe a little bit above these green values. But There's a lot of significant, well, within the error bars it agrees. There's uncertainty here, there's uncertainty here, but it looks like we're going in the right direction. And these calculations actually can give you something that corresponds to experiment.
Is zeta hat, sorry, or yeah, zeta hat, is that your rapidity regulator?
Yes.
So at what stage would you expect the regulator dependence to finally cancel? Is this not the observable?
Well, the way this is set up, the contact with experiment is made at infinity.
Okay.
Yeah, this is maybe a bit complicated to I'll try to do it with hands. So what Collins defines, Collins' definition of TMDs is the bilocal quark operator that we're looking at here. Okay, yeah, so people can see my arms. Right, so our quark operator here has a staple that goes in a certain direction. Okay? And then Collins has the soft factor, which is a concatenation of two staples. One of them exactly matched to this, and the other one going into another direction. And Collins' zeta characterizes this direction, whereas this direction is being let go to infinity. And so if I want, and so what I'm doing is I'm calculating quantities where the soft factor has canceled, but in order to make contact with what Collins says, I have to let this one go to infinity. So that's why I'm saying my data here make contact with the experiment in the zeta hat going to infinity limit, because that's how Collins defines it.
Thank you.
And yes, indeed, the quantities we're defining are by construction independent of Collins' zeta. They are Collins zeta invariants by having formed the ratio and having divided out the soft factor, which is where the zeta dependence would come in. Yeah, in the paper where we originally showed this, we made a plot that's easy to misunderstand. We put this value at a certain zeta hat, even though the zeta hat is not the same thing as the zeta. So yeah, that was not the best way to present it. But anyway, so therefore here I'm just telling you the value and showing you that. Look where it belongs. Okay, just as an aside, let's erase this green thing and use the green symbols for something completely different. So now the green symbols mean something completely different. All I want to show here is that apparently these quantities don't significantly depend on the pion mass, because that was a question before, right? So what this is the same physical pion mass, blue and red data as before at these two zeta hat. And what I've overlaid now is older data at 300 MeV pion mass at an intermediate zeta hat. So the green data are at the intermediate zeta hat, 0.41, but they're taken at 300 MeV pion mass. And they exactly fit in between here where you would think. So that there seems to be no dependence on the pion mass here. And it's as though there were no pion mass dependence. The 0.41 data here at the higher pion mass, they just fit right in. Nothing dramatic seems to be happening. And that's not something that we could have predicted before. There are many quantities we calculated in Lattice QCD which strongly depend on the pion mass. For one important example is simply the momentum fraction, the unpolarized quark momentum fraction of a proton. It dives like by a factor 2 as you approach the physical pion mass. So this is not something that was expected a priori, but apparently the Sivers shift doesn't really depend on the pion mass. Okay, so let's go on, and maybe I should go through this quickly. So all my discussion up to now was for the Sivers shift, and of course we have all these other ones, and I'll go through it quickly because yeah, maybe this might become a bit redundant. One can do it for the Boer-Mulders shift. There, the signal isn't so good, and that's because I'm always doing isobector U minus D quarks, and for the Sivers, U and D have opposite signs, so when you subtract them, they add. Whereas for the Boer-Mulders, U and D have the same sign, so when you subtract them, you subtract you do a difference of larger numbers, and so the signal isn't as good. You can again do the dependence on BT like before, and it doesn't look so much different. You can do a dependence on zeta hat. So here I'm not doing extrapolations, I'm just showing the dependence on zeta hat doesn't seem to be particularly strong. Transversity, okay, so here we have a T-even quantity, and we can again do a movie. Here the quantity rises a bit as you increase the BT. And you can again summarize that. There's a slight rise. As I said, in the limit BT going to 0, this should just be the tensor charge. And yeah, the ZT, but you need to multiply by the ZT, by the tensor renormalization constant, which is close to 1. So this is consistent with calculations directly of the tensor charge. Zeta dependence, Boer-Mulders shift. Okay, here we have an example where, yeah, at moderate B, you already really start to get into trouble with your plateaus. But again, so you can do this for all these different shifts that we defined. Further systematics, and maybe I'll go through this quickly. As Fiala already indicated, excited state contaminations are important, especially as you go to lighter pion masses, because correlations become more long range. So I'll show you one quick slide or two about the excited state contaminations. Fiala also mentioned operator mixing. Yeah, operator mixing is an issue. We form these ratios. As long as that's one operator, one correlator over one correlator, all the soft factors and the renormalization factors cancels. But what if there's operator mixing? That means that in the numerator, you don't just have one factor. In the numerator, you have a sum. You have all the other mixtures of other operators. So you have a whole sum in the numerator and a whole sum in the denominator. And of course, you can't cancel stuff between sums. Are there any German speakers here? Aus Differenzen und aus Summen kürzen nur die Dummen. Which, yeah, out of differences and sums, only fools cancel. So yeah, operator mixing will invalidate this whole scheme of canceling in ratios. So that can be a big problem. So yes, Fiala already explained, you have to make the time differences large enough to get rid of excited state effects. And so we tested that in these new data. Also, this was not available for older TMD calculations. This is also new. And the excited state effects seem to be very mild. So this is again the Sivers shift. And the different colored points here are just taken at different source sink separations to see how things converge as you take the positions apart in temporal direction. And it seems mild. So the excited state effects don't seem to be a big issue here. At some point you lose signal, of course, and things go haywire. But we now also, for the first time, have control over that systematic. We did not have control over that systematic before this new calculation. Right, so now the operator mixing. So what we did this empirically. We took two calculations at basically the same pion mass. So this should really be the same physics. We took an ensemble of domain wall fermions. This is a really, really good but expensive discretization, which respects chiral symmetry. And if you respect chiral symmetry, you may get rid of all operator mixing. A lot of up to now, it seems as though the operator mixing is mainly caused by breaking of chiral symmetry. And so we use here on fermion discretization that respects chiral symmetry at pretty good lattice spacing. And we compare it with a Clover ensemble, which badly breaks chiral symmetry and at a coarser lattice spacing. So this is a really good discretization, and this is a really crappy discretization. And so we think when we do calculations, effects of operator mixing should show up in the difference between these. And so we tried this out, and for a while things look pretty good. So this is the Sivers shift again, and there's the domain wall and the Clover, and it all looks pretty parallel. Yeah, nice. Let's put together this BT plot. The data seem to coincide. Okay, here they're a bit jumpy, but within 2 sigma, nothing really to worry about. So Sivers also as a function of zeta, everything seems fine. Boer-Mulders.
Why does the minimal have consistently bigger error?
They're more expensive and therefore you're only able to do lower statistics. It's simply statistics that you can afford it. Yeah. Also here, so for the Boer-Mulders, nothing bad seems to happen. Transversity, seems to go fine. Worm gear shift. Okay, there seems to be something happening down here, but yeah, you expect discretization problems here anyway, so I'm not worried too much. Also, as a function of zeta hat for one of the larger ET, looks fine. Okay, and so we thought, well, okay, let's look at this in more detail. A lot of the an issue here is, of course, that the error bars are so large that you probably just don't see effects if there are any there. A lot of the large error bars come from the large areas of those staples. Let's do a straight gauge link just to see what happens, because a straight gauge link data will be much more accurate. So this is now the transversity again, same as before, except with a straight gauge link, and it agrees beautifully, even when you when you suppress the error much more strongly, agrees wonderfully. And now let's do it for the worm gear shift. Whoa, here's something happened. So this is the worm gear shift, which already had some indications of funny stuff happening at low BT, but now for a straight gauge link, and now there's a clear discrepancy. And we interpret that as a signature of operator mixing. And in fact, there was a lattice perturbation theory calculation by Martha Constantino and collaborators, which showed what the pattern would be, which operators should mix. And what we see here is exactly one of the channels where they predict we should see something. So that makes us think that this is one of the instances where really something goes wrong. And I would say in this picture, you should only believe the red data because they're domain wall and don't break chiral symmetry. And the blue data are probably simply wrong. You've canceled stuff in a ratio that you really shouldn't cancel. And Fiala, in fact, made and collaborators did a more detailed investigation non-perturbatively. And these are the patterns of operator mixing they find. So this is the axes are the gamma structures. And of course, the strongest is on the diagonal. But everything that's not black on the off diagonal is operator mixing. And these white dots are the mixings that were already predicted by Constantino et al. In perturbation theory. And Fiala sees that if you do this non-perturbatively, or in other words, go to higher order, there's even more mixing. So eventually, this is an open job that hasn't been done. Eventually, one would like to take these mixing matrices and reconcile these data. It should be possible. You should be able to take the full mixing matrix and assemble the correct ratio, and then these data should coincide again. That's an open issue, and we just haven't found the time to do that. But eventually that should be done to really make sure that we're understanding what's going on.
Yes, so you're able to make that mixing matrix essentially cheaper calculations to get the same results.
Yes, it would enable you to use the Clover fermions, and that would be cheaper and therefore more accurate. Yes, that would be a benefit of doing that. Yes. Yes. It depends. So, well, in these ratios I'm calculating, these are renormalization group invariants because the ratios are exactly meant to cancel the renormalization factors. But if renormalization factors don't exactly cancel, then usually what happens is you do an intermediate scheme, a lattice scheme, for example, called RI-mom. And then in the continuum, you in a second step calculate the matching factor between this RI-mom and the MS bar. And then you have something that phenomenologists can relate to. So it's usually a two-step process.
In that analysis, are you looking at ratios of their correlators?
Sorry?
In your analysis, are you looking at ratios of their correlators?
Ratios of what? Oh, bare. Yeah, yes, everything is bare. And so the idea is that in the ratio, the renormalization factors cancel. Yes, that's what I'm doing all the time. I'm never calculating the renormalization factor. I'm always constructing a quantity where they cancel, and therefore I don't need them. Yes. And so certain quantities. Yes. Okay. So we should move on. Right. There's a bunch. So okay. So this completes the discussion of the basic TMD program, which we've been doing for 10 years and just been refining. And we're now at the physical pion mass. We now control systematic effects much more than we did 10 years ago. So this is sort of the core TMD program. And now I come to a few other things, spin-offs, which are physically also very interesting. And so you're saying I have 15 minutes?
Yes.
Then I should go through this quickly. So one central question in hadronic physics, right, is the proton spin puzzle. And there are two important decompositions. Of course, in principle, there's infinitely many decompositions of proton spin, but ones that are discussed a lot are the G one and the Jaffe-Manohar one. And there's gluonic parts, and I'm not going to say anything about gluonic parts. But on the quark side, there's the quark spin, which is the same between the two, and there's quark orbital angular momentum. And for quark orbital angular momentum, we can do something new here, because we now have a way of getting the quark momentum information. All we have to do is add quark position information. And then I conform R cross P. Then I conform orbital angular momentum. So how do I get the quark position information? Let's leave that for now. So let's imagine we have a Wigner distribution, which gives us the distribution both of quark momentum and quark position. If we had this Wigner distribution, then we could calculate the average of R cross K. That would be orbital angular momentum. That would be a direct calculation of orbital angular momentum. Without this, traditionally lattice calculations of quark orbital angular momentum were never directly L. They were always J minus S. You calculate J from G's sum rule from the GPDs, and you calculate the spin, and you form J minus S. That gives you L. This is a way of directly calculating L and verifying that the sum rule actually works. And so how do we get this information? Well, we already know how to get the momentum information. How do we get the position information? Well, the position information, well, what we need here is the impact parameter. How far from the center of momentum of the proton are you? And what is the impact parameter Fourier conjugate to? The impact parameter is Fourier conjugate to the momentum transfer in your process. So this is the same matrix element as we had before, except I'm now allowing for a different momentum in the final state than in the initial state. So almost all the ingredients we needed, we already have. We have this nifty TMD operator that extracts momentum for us. And all we have to do is generalize to non-zero momentum transfer, which is Fourier conjugate to impact parameter. And then we have this Wigner function. And we can calculate orbital angular momentum. And so what I need to do is I need to take this matrix element, now with P prime not equal to P. I take a derivative with respect to momentum transfer. That gives a factor of R in position space. I take a derivative with respect, I'm calling it Z instead of B here. I'm not going to explain why, but there's a reason. I take a derivative with respect to Z, the operator separation. That's, of course, the K. I combine them as a cross product, so I'm forming R cross K. So I need to do basically the same calculation I've been doing all along, except with a momentum transfer, take these derivatives, and I've got orbital angular momentum. And there's, of course, again, the question of the choice of the gauge link. And here, both the staple link and the straight link are physically relevant. The straight gauge link gives you G orbital angular momentum. The staple shaped gauge link gives you Jaffe-Manohar orbital angular momentum. So this formulation actually allows you to access both and even interpolate between them. So let's see what happens.
So
Yeah,
it'll
and
still be perp, but you're just drawing a straight line between the 2 points.
yes. Yeah. And so again, I have to normalize this. So I normalize it same as before, essentially. I normalize it again by the unpolarized matrix element, which, right, and okay, so here's where the tricky thing happens. So if I want to integrate overall KT, overall momenta, that means I have to let the separation Z go to 0. And I'm not writing equals here, I'm writing an arrow here, because that's the tricky part. Letting Z go to 0 is where the divergences happen. And so I'm doing this with a grain of salt, but I'll show you something at the end. So you have to take this tricky limit operator separation Z going to 0. But okay, so there's some trickiness, but if I form this ratio, then again, renormalization factors, I think, cancel. Let's just try it out. Let's do this. Yes, I already mentioned we can get both G and Jaffe-Manohar. Again, we have a zeta hat, right? For the G, there is no actual V. For the G, I have a straight link, and there's no actual direction V that enters the calculation. So the straight link calculation should actually be independent of zeta hat. And yeah, I need to take these derivatives and I'm doing this in the best way possible. And I'm mentioning that this limit that we're taking is not, there's a divergence, and what I'm showing is not identical to MS bar. In principle, there would be a matching factor, but let me show you the data. So here, G, so this is eta equal to 0. This is the straight gauge length. This should be the G value. I'm showing you different zeta hats, well, which formally is just different momenta, but the quantity should be independent of zeta hat, which is why I fit a straight line through it, I fit a constant through it. And so I have 3 values, and this blue point here is my extrapolation to zeta going to infinity, which, well, is just the average of these points. So the blue point here is the result from the method I just described. The red point here is a traditional calculation from G's sum rule, J minus S. And that's done with local operators, and we know how to renormalize it, and we know how to convert it to MS bar. This red data point is MS bar. Red is MS bar. Blue is this funny scheme where we're a bit worried about the ZT going to 0 limit. They agree perfectly. So apparently these matching factors that we're not quite sure how to put in here, they seem to be very, very close to 1. And recently, Ian Stewart and collaborators actually put out a paper where they give a bit of an analysis of this, and they justify that taking these ratios, where I control everything by a Z that I take to 0, what this basically means is I'm cutting off the transverse momentum integrations at the resolution scale, which is a very physical thing to do, right? I mean, you're doing your field theory up to some resolution, and now somebody tells you, hey, take a momentum integral. Of course, you're going to cut off the momentum integral at that resolution scale. You don't have information about higher scales. But it's a very physical thing to do. And Ian Stewart and collaborators argue that if you do it like that, you're doing something that's very close to MS bar. And the matching factor should be very close to 1. And this corroborates that. I mean, we did that. Here's the MS bar value from a completely different method. Here's the value you get when you do this TMD type calculation. It works. Of course, this is empirical, but there are reasons why this should work.
So what is the N of the denominator?
That's the number of valence quarks. That's what I was,
okay.
Yeah. It's just the correlator without weighting. So yeah, so for me, in this calculation, the renormalization condition is that the denominator becomes 1. It's U minus D, so it's 2 minus 1 quarks. So the renormalization, of course, in the lattice calculation, this is some number. And the renormalization condition is this is set equal to 1. And that's how this renormalized quantity here is defined in this scheme. And this scheme is not the MS bar scheme. It is a scheme. It's not the MS bar scheme. Apparently the difference is very minor. Okay, but now we can also go to non-zero eta. And here's what it looks like. So I'm normalizing this to the G value, so to the magnitude of the G value. So at 0, you have just -1. It's negative. I'm normalizing by the magnitude, so it's -1. As you increase the staple length, it becomes stronger. You have more orbital angular momentum. The final state interactions introduce torque that increases the orbital angular momentum. And we can do this for 3 different zeta hats. So apparently the effect increases with zeta hat. So it's fair to assume that the extrapolation to infinite zeta hat will give a finite value. It doesn't go to 0 because it seems to be increasing. And so here you're literally watching a quark being kicked and leaving the proton and gathering up more torque. Gathering up more torque as it's leaving the proton until it reaches the Jaffe-Manahar orbital angular momentum once it's outside. And this is the gauge invariant interpolation.
So is it bothersome that that isn't symmetric?
That's no, those are numerical fluctuations. I mean, by construction, this matrix element is symmetric. Just again, use parity.
That's numerical.
That's a numerical artifact, yeah. And you would be perfectly within your rights to simply average over the 2. And in fact, when I plot the infinity values here, actually that is the average. You see the black plateaus I formed here. The values are infinity are the average between the 2 black plateaus. And that's perfectly correct to do because the quantity by definition is symmetric. So that's just numerical, yeah. Okay, so we can do something about the proton spin puzzle here. Let's move on. I can do it in a flavor separated way. One can also do spin orbit correlations. All I do is I put in an extra gamma 5. So now I'm calculating orbital angular momentum weighted by helicity. And you also get a nice, you get very strong, this is a very new calculation. You get very strong spin orbit correlations in the proton. So it looks, if you think of atomic physics, it looks like JJ coupling, not Russell-Saunders coupling. Yeah, so you can do all the spin physics. You can do this proton spin puzzle physics. I think I should not show this. So up to now, I'm only going to say briefly what's happening here. Up to now, I did everything at b longitudinal equal to 0, in other words, integrated over x. But of course, nobody stops me from scanning the longitudinal b direction. Yeah, before b dot p was set to 0. But nobody stops me from scanning the b dot p direction and Fourier transforming and getting the x dependence. And so this is a preliminary sketch of getting the x dependence of the Sivers shift. And I'll just show you the end result. So this is completely quick and dirty and preliminary, but you get a plot like this. So it's multiple. So this is the Sivers shift multiplied by x, because that's what all the phenomenologists do. So I grant myself also an x here, because at low x you anyway don't trust the lattice calculation. And you get the Sivers shift. Of course, it runs beyond x equal to 1 because we're at finite momentum. We're not at the infinite momentum frame. Lots of systematics here still to be taken care of. The U quark is worse than the D quark, but it's a proof of principle. You can do this calculation. One can get the x dependence of the Sivers shift by using this scheme. Collins-Soper evolution kernel. The idea there is simply don't take ratios of TMDs at different spin content. Take ratios of TMDs at different momentum, because that's exactly the dependence on zeta. Just looking at how do things change at different momenta. And the first calculation of this, and so this was worked out by Abert, Stewart, and Zhao, and then Fiala did the first calculation of this. So yes, so SWZ here is not Schiffman, Weinstein, and Zafarov. It's Shanahan, Wagman, and Zhao. And they did the first calculation of the Collins-Soper kernel. And I think that's these blue data. And then subsequently, there were a couple of other calculations. And well, there is still some systematics to be understood. But roughly speaking, we have a first idea of what the kernel behaves like. We don't at this point see any quadratic behavior, which is one of the options that was discussed phenomenologically. Hey, maybe it happens at larger B. For now, this is what you get from the lattice with large uncertainties for the Collins-Soper kernel. The soft factor, yes, finally the soft factor. What was the issue? The issue with the soft factor is it's made out of two staples stuck together, and these two staples have different rapidities. And now you have a problem, because there's no way to boost this thing to a Lorentz frame where both of the staples are purely space-like. You can always find a Lorentz frame where one of them is purely spatial. You can always find a Lorentz frame where one of them is purely spatial, but then the other one will be going off in some direction. You can't make this purely spatial. So at the basic scheme that we've been using up to now, you cannot calculate the soft factor. But the idea, the solution to that is stick the staples into the states, because physically, what are these staple legs? These staple legs are Eichenal propagators of hard quarks. If they were going purely in the time direction, they would simply be infinitely heavy quarks. They're of course not going into the time direction. They're moving very fast, close to the light cone. That just means you've kicked them really hard. And that's the interpretation of the original TMD correlator in any case. So you can think of this staple here as a state, as a hard quark state, and this staple here as a hard quark state. So you can stick the staples into the states and only leave these connection points, these connection vertices as the operator. These connection vertices you can perfectly well put at one time, no problem. And states we can boost. We can easily have this one state boosted in one direction and this other state boosted in the other direction. So this is not lattice calculable. This is lattice calculable. That's the idea. Now in practice, and so this was worked out in more detail by Zhang Dongji and collaborators. In practice, you don't actually use these hard quark states. There's other problems with that. But you say, well, basically I'm doing a meson here. It's a quark, anti-quark, yeah, going one direction, other direction. So probably the same information should be contained in just doing some meson-meson correlator. And so they worked out how that works. And so they're just doing a very strange meson-meson correlator. Here you've got a meson, here you've got a meson, and it's a meson-meson correlator where both the quark and the anti-quark are instantaneously kicked, in coincidence. In coincidence, you're kicking at this vertex and this vertex, you're kicking both the quark and the anti-quark in exactly the same way. So this is not something that would ever happen in an experiment. But it's a quantity you can define, and you do this funny meson correlator where you coincidentally kick both the quarks, and that contains the information about the soft factor. And so there's a first calculation of that, and this is the result they got, the lattice parton collaboration, which includes Zhang Dongji and collaborators. So this is now a perspective of going beyond ratios, and that's the new thing. With the scheme I explained before, you always have to form a ratio to get rid of the soft factors. Now that there is a way of calculating a soft factor, you may be able actually to calculate the entire glorious TMD with all its dependencies and all its evolution and everything. So that's the advance that comes from here. So those are the perspectives. This is the last slide. This quasi-TMD framework has been developed recently, and the people who've done this mostly are Ian Stewart and collaborators, and Zhang Dongji and collaborators. There aren't many results yet from this approach. The only two things that we have up to now are these calculations of the Collins-Soper kernel and the soft factor. There's no actual TMD yet that has been calculated with this approach, but certainly it's a bright perspective because doing this will allow us possibly to go beyond the observables that I showed up to now. So yeah, I hope I've stayed within my time.
Close enough. Thank you, Michael.
You're showing us what some TMDs actually might look like by the end of the school. So. We can take some questions.
Just want to ask about the difference between summation rule and Manhart, that you take the ratio on the y-axis, let's say, and TM or xi, I think on x-axis, right?
Let's see. Let's find the plot.
Yes.
I think you want this one. Probably.
Yeah.
Yes.
And somehow we can write out the ratio in terms of A amplitude, right?
The ratio in terms of what?
A amplitudes, A to B and
yes, that's right. So yeah.
my question is, does changing of psi means we are changing the number of A's or the amplitude of A's, the width of the amplitude?
We're changing the argument of the A. So right, so let's go back to one of them.
The same thing here, yeah.
Yes, so somewhere, right, so you see here, these A amplitudes are functions of all the different, well, here they're not written as invariants, but they're functions of the different parameters we have. And one of the arguments of the A amplitudes are the hat, so these are functions of however, yes, at eta equal to 0, they must be independent of zeta. Yeah, that's true.
So in the other what we are changing A's. This one.
Sorry, you want one of these?
Yeah. Oh no, the other one.
You
The next one.
You want the orbital angular momentum again?
Yeah.
Yeah.
No. Sorry. The one which you changed the pair. This one.
The one where I changed the curve.
Yeah.
Okay. So in this orbital angular momentum discussion, I've always taken that limit b going to 0. So these are all in the b going to 0 limit, and we've discussed how tricky that is. The TMD data I showed before, they were all at finite b as a function of b. Yes. Whereas here I'm taking the b going to 0 limit with all its caveats. Does that answer your question?
Thank you.
And yeah, I mean, there's of course this empirical point that apparently I've taken the b going to 0 limit reasonably correctly because these that's an empirical statement. And as I said, Ian Stewart has arguments why it should work. But there's a it's non-trivial difference.
So, are you choosing a or choosing AT?
Yes. Right. It's in principle, it's done as a function of ET. And what I showed, right, and in fact, the raw data here that I'm showing. So these would be typically raw data, and the axis is the BL. The different colors are different BTs. So I'm investigating the whole BL BT plane. Then I do analysis, and what I showed here at the end is again this should be sort of the low to medium BT behavior. I'm not showing dependence on BT anymore. But this is supposed to be the low.
There are kind of then we have a finite limit.
No, but I think the Sivers ratio should be particularly well behaved in this respect because the two quantities that go into this ratio here, the A12 and the A2, they come from the same correlator. It's exactly the same correlator, and you just look at the real and imaginary values, and you take the appropriate weighting with B or K. And if you choose that combination of the two quantities you're using here, if you choose the right combination, then the B going to 0 limit should be finite. This is something that Ignacio Shimenian showed some of these things. So I think I'm taking the right combination here that has a good limit. Okay. It is an issue. If you just do anything, you'll get divergences. You have to do the right thing to have a stable behavior. I guess the zeta hat here, it's, yes, I think it was something like, yes, very low. And you saw in the TMD plots, you saw how the extrapolations work. There is significant dependence, but if you work hard enough and get a range of data, apparently you already start seeing the power law 1 over p behavior starting at fairly low zeta hat, which is also not trivial. This would not be expected. And but yeah, I mean, a priori, I was not sure whether this kind of thing worked. It could have been that the behavior here is not nicely 1 over zeta hat. It could have been that this is some funny curve behavior. But actually, it turns out, yeah, 1 over zeta hat is 4. This is 0.25. Zeta hat equals 0.25. Already falls into the range where it looks like it's essentially, which is very lucky. It could have been much worse. But it looks like we're lucky that the control starts the onset is very low.
It has to narrow it down.
Oh, okay.
Well, thank you, Michael.
Right then.